For more information, please visit SGMAK Associates website.
We test hypotheses for distribution parameters only. We never test hypotheses for a statistic. For example, let's say you have developed a new type of engine that is supposed to deliver 40 miles per gallon. You want to test the hypothesis. We'll set up null hypothesis as mu, the mean mileage per gallon, equal 40. The alternate hypothesis is set as mu not equal 40. We develop a few prototype engines, run them, collect results, and analyze it to check if it is consistent with the null hypothesis. We ask the basic question, how would the data look like if the null hypothesis is true? We test the results with respect to the null. We either reject the null hypothesis or we fail to reject the null hypothesis. We decide in favor of alternate hypothesis when we reject the null. We make two types of error in testing hypothesis since you're working with the limited information, a small sample. Two types of error are type 1 error. We make type 1 error when you reject a hypothesis that is true. Rejecting a hypothesis that is true is the type 1 error. We make type 2 error when we accept a hypothesis that is false. We make both types of error in testing a hypothesis since we are working with a limited sample, limited information, typically small sample size. Our objective, however, is to control both types of error. So in reality, what we do is we specify each type of error and then design the sample size to meet this requirement. We'll discuss it later. We perform either one-sided test or a two-sided test. One-sided test can be either a lower-tailed test or an upper-tailed test. For example, if we set null as mu equal 40 and alternate mu not equal 40, this is a two-tailed test. If we set null mu equal 40 and alternate mu is greater than 40, is an example of an upper-tailed test. And if we set null mu equal 40 and alternate mu less than 40, is a lower-tailed test. The problem statement will decide the nature of hypothesis that you have to test. Let's take an example. We want to test the hypothesis that the true melting point of an alloy is 750 degrees Celsius. True melting point is 750 degrees Celsius. The melting point must be on target for successful subsequent operation. So we are concerned about melting point being higher or being lower. We want to keep it exactly on target of 750 degrees Celsius. We assume that the melting point is normally distributed random variable. We assume a probability of type 1 error is typically represented by alpha. We set that as 5% or alpha as 0.05. And based on prior knowledge of the process, the standard deviation of the process is 10 degrees Celsius. Now we take a random sample of 25 observations. We are selecting it arbitrarily right now. Let on give an example where you design the sample size. We select a sample size of 25 and let us test the hypothesis that the true melting point meets the requirement. So we set up the hypothesis as null mu equals 750 and alternate mu not equals 750. It's a two-sided test because we want to keep our target of 750 is of interest to us. The basic question we ask in testing a hypothesis again, how should the data look like if the null is true? We compare the expected behavior of the sample average, if the null is true, with the observed data at the specified level of significance. So all is the basic premise is how should the data look like if the null is true? we compare expected behavior with observed results. Now for convenience, we'll use accept null and fail to reject null interchangeably in this document. The rejection region for null hypothesis, we will be rejecting null if x bar sample average is less than 750 minus z.025 sigma over square root of n, that's on the low side, or if x bar is greater than 750 plus z.025 times sigma divided by square root of n, that's on the high side. We fail to reject the null hypothesis otherwise. In this example, we have a sample size of 25, sigma is 10, alpha is 0.05. So if you compute, we get our bounds as, we'll reject the null hypothesis if x bar is greater than 753.96 on the high side, or x bar is less than 746.04 on the low side. So that's our decision rule. We set up the decision rule before we collect the data. Now we got a random sample of 25 and gives us an average value of 755. So we use the decision rule, and in this case, we will be rejecting the null hypothesis in favor of the alternate hypothesis because the observed sample average falls in the rejection region of the null hypothesis. Or we say that the observed data do not support the null hypothesis that mu is 750 at 5% level of. For a two-sided test with a level of significance alpha, the fail to reject null hypothesis region is given by mu naught plus minus z alpha over 2 sigma over square root of n, where we set up null hypothesis mu equal mu naught. This is based on the requirement that the probability of x bar falling in the rejection region given the null hypothesis is true is alpha. For a two-sided test, we split alpha equally on each side. Remember, if x is normally distributed with mean mu and standard deviation sigma, then the sample average x bar based on a sample size of n will follow normal distribution with a mean mu but a smaller standard deviation given by sigma divided by square root of n. This example shows how to perform a two-sided test on single mean. The level of significance must be selected by the decision maker prior to data collection. Since alpha represents the probability of making type 1 error, reject null hypothesis null is true, a small value is selected. We have arbitrarily selected a sample size of 25 in this example, and because of that, we have no control over type 2 error. Later, we'll discuss how to estimate the sample size that meets both type 1 and type 2 error requirements.
For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website.